Hmm? Oh, wrong class. There we go. Well, the mic is okay. The mic is on, but the amplifier was not. So that's why. There we go. And OBS is streaming with audio. That's good. All right. So what we'll do today is I will get you guys started with the ABS or absolute value homework assignment. It's already active for one member of this class because he's actually going to the Monday, Wednesday class and lab, even though he's enrolled in Tuesday, Thursday. So I'm going to start with a preview of this particular new lab assignment, just so that I make sure that I talk about the topics that I need to go over. So the absolute value is really just the magnitude of a number. So if you're dealing with the absolute value of 20, it is 20 itself. If you're dealing with the absolute value of negative 16, then it's 16, because it is the magnitude that matters when you look at the absolute value. So one way to implement absolute value is like this. Okay, if x is less than 0, then you return the negation of x. If x is at least 0, you just return x itself. So that's one way to implement absolute value as a C function. So are there any questions about this? Nope. Okay. And then the questions, basically brings back, the signed representation, what it means, what is the which bit indicates that the value is negative and stuff like that. So I'm not going to give you the answer, but I can tell you that we have already talked about it in the module that talks about signed versus unsigned representation. The second one is to check the sign bit, and so on and so forth. And the question is asking which bit from the ALU reflects the sign of the result of a computation. Once again, I'm not going to give you the answer. The answer is actually somewhat obvious. But if it is not obvious to you, then you need to go to the ALU component of the toy processor, expand it, look at the flags out port, and then figure out what each one of these bit is going to, and then from that figure out where is the which one reflects the sign of a number. Okay. So once again, this is something from the previous semester. It is also in the processor design itself, so you can find the answer from one of those two sources. So now the question, this part is asking which instruction is hijacked, because there's no need for some of the combinations of the instructions. So by means of instructions that do not really do a whole lot of useful things, we are talking about something like AND AA. So if you look at AND AA, what it's doing is it really is just doing the same thing as A equals to A bitwise AND A. But A bitwise AND A is always just A itself. So this particular instruction or mnemonic doesn't really do a whole lot of useful things. Okay. However, anything that is coming out of any computational module inside the ALU has to go through, will set and reset certain flags. They affect certain flags. So the 0 flag is one, the sign flag is the other one, that is always affected by whatever operation that you're passing through the ALU. So that means a side effect of something like this can be quite useful when you just want to use the register A to affect some of the flags. Okay, but at the same time, I don't really need AND AA as well as OR AA at the same time, because they can do exactly the same thing. So that's why the opcode, the binary opcode of some of these is quote unquote hijacked. When I say the word hijack, it simply means that it is now used for something else. The opcodes table will give you the answer to this question. So what you need to do is to go to the opcodes table. Okay, let me go to the opcodes table first. and it's under opcode table. And we just have to look up the opcodes of AND, OR, and then we just need to find out whether there's an overlap from other instructions with that particular opcode pattern. So here we find AND as well as OR. Let's see, we find AND, and OR is right. Oh, this is add. Where's AND? Scroll down a little bit more. There we go. So we got AND and OR down here. This is AND, and this is OR. Let me magnify this a little bit. All right, so here's, I just did something. There we go. So this is AND and this is OR. So this means, every single AND instruction is going to start with the upper 4 bits being 1100, and every OR operation is going to start with 1101 as the most significant 4 bits. Well, what about the other 4 bits? Well, the other 4 bits kind of depends on which 2 registers are you ANDing, or which registers are you ORing. So if you're ANDing A with A, that means X6 is going to be 00, Y is going to be 00 as well. So as an entire opcode, that becomes 1100, 0000. Okay? Same thing for OR. Okay, so if you're ORing A with A, then it becomes, the binary opcode becomes 1101, 0000. Is that okay? So if you find in here, there's another opcode that has exactly the same pattern as one of the ones, in this entire family, that means that particular instruction is quote-unquote hijacked. The opcode is hijacked for something else because that particular combination for AND or OR is not useful. But I only have hijacked one of the 2 because the other one I want to leave it as is so that I can easily test for the sign flag and 0 without having to use the actual compare instruction. So your job is to figure out, I think the question is asking which one is hijacked. So let me just double check with the question itself. Okay, so TAC remembers the opcode of either the AND or the OR family is hijacked for other instructions. Analyze the opcode table and find out which one is actually hijacked. So that's basically what you need to find out. So are there any questions about this one? Nope. Okay. So moving on to, this is question number 4. Combining the results of the previous 2 steps, so you got to kind of go back and look at those things. Now we have an efficient way to test whether the sign bit of a register is set or cleared. There's no such instruction, there's no such mnemonic called test. In other words, test here really should be AND or OR, okay? The one that has not been hijacked is the one that you need to put here, so that we can easily test whether the sign flag is set or cleared, and it will also even tell you whether the number is 0 or not, but that's not what we are looking for in this particular homework assignment. The second instruction is JSI, because we are looking at the sign flag to see whether we should branch to L1. If we do branch to L1, that means the sign flag is a 1, and we need to do some certain operations. Otherwise, we continue execution because the sign flag is a 0, so we will do something else. Okay. So at this point, you need to write some code, assemble it, and test it in the simulator to make sure that this sequence of mnemonic does work as expected. So that means just write out these opcodes, assemble, and run it in the simulator. You might need to add some halt instructions and put a label definition somewhere, but the idea is you just have to make sure that this combination of instructions does differentiate whether the sign flag is a 1 or 0 from a particular register. And before you run this code, you obviously also have to set a particular value in the register. So in this case, if I use A for X, then you have to inject a value into register A, test it with the most significant bit set, and test it again with the most significant bit cleared, so that you can see whether the conditional branch is steering the execution of the program to the right place. Okay? So that will help you understand and confirm your understanding of how this part works. So once you're done with this code, okay, you're now ready for the next step. So the next step is, if the number is negative, then you want to do something like this. And by the way, this part here is not a minus, it is the tilde symbol. The tilde symbol in C means bitwise not. In other words, we are performing a bitwise not of a particular bit pattern in the register, and then we're adding 1 to it. What is that called? Okay, that's what the question is asking. I'm not going to tell you, okay? So you might want to kind of revisit some of the previous modules if you want to figure out what is the name of this operation as a whole. I believe that was talked about in the discussion of signed versus unsigned representation. So that's one thing you want to investigate. And then the last question is the part where I ask you to do the entire program. So even though it seems like this part is the only part that I want you to do, the actual thing that I want you to do is all the way back to question number 1, which is the entire code to find the absolute value in a register. So you make an assumption and you say, okay, let's say the value that I want to take an absolute value of is in register A. So now you have to write out the entire code to test whether the value in register A is negative or not. If it is negative, then you have to negate it, arithmetic negate it, and then in place, which means that the absolute value has to be stored in register A as well. If it is not negative, then there's really nothing to do. You can just halt right away. Is that okay? So that's what you need to do, and I want you to copy and paste the actual mnemonics into this area, not the opcode, but the mnemonics. So I want instructions like JSI, okay, halt, label definitions, that sort of thing in this area. So that's our entire new lab. You have 1 week to work on this. Some people got it done within like 30 minutes, and other people may need a little bit more time to review past material of what is that tilde x plus 1, or where the sign flag is and stuff like that. So look at this as an opportunity to study a little bit of things that I think you should know already. If you're forgetting something, no big deal. Just go back to the previous modules, look it up, study a little bit. You can even Google. I mean, you can even Google and see if you can find something related to the questions. And just kind of do it slowly so that you absorb the material by doing this assignment. Okay, well, it's kind of like a lab activity, but it's also an assignment. So do we have any questions about taking the absolute value of something in a register? Is that part okay? No questions? Okay. So if you do have any questions, we can handle those questions at the lab. Okay, so you can show me what you have, and ask me, okay, I'm not really sure what this is doing, or you can ask me about, what am I supposed to do with this part of the question, I can clarify when we are at the lab. Is that good so far? Okay. All right. So if that is all good, then we're going to start on a new topic. And let me do one thing before we get there. Okay. Oh, it doesn't give me a quick way to get back to the top part of this activity. So I'll just edit here and give you the due date of this assignment. So we'll assign it to everyone, and the due date is next Tuesday, sorry. So next Tuesday is the 6th. Okay, so this is going to be the 6th as well, and is available from today, which is October 30th. There we go. And the passcode, by the way, is ABS, just absolute value itself. Okay, save. All right, so that is done. So now we go back to the modules, and we'll start to talk about how to call a subroutine and how a subroutine is supposed to return back to the caller. So that's going to be our next topic. And the next topic is right here, calling and returning from subroutine. Sounds pretty easy, okay, in C and C++, but the concept actually is a little bit interesting, okay? A lot of stuff you're not seeing when you're working with a C or C++ program. So this is the module that I'm going to focus on today, and I believe we have enough time to finish the entire thing today. So there are a few key concepts here. The first key concept is, well, I'll first present the C program first. I'm hoping that this does not look mysterious to anyone. Everybody knows that what it's going to do. It doesn't do a single thing that's useful, but it does help illustrate what calling and returning is about. So when you execute this program, the first thing main is going to do is going to call f the first time. So when you call a subroutine, then it's going to continue execution in f, which has nothing to do. So f will want to return. So now the question is, where is f returning to? Well, f is returning to the second line in main, because now it continues execution in main. Well, that turns out to be another call to f, so now we continue execution in f again. F has got nothing to do, it's ready to return again. When it returns this time, where do you think f is returning to? To the return 0 statement, because that's the last thing. It's the next thing right after the call to f. So we kind of know the behavior of calling and returning, but we don't really know how it can do this. Okay, because if you think, oh, I'm guessing at the end of f, we just have a jump back to a certain point in main, then it wouldn't know that the first time it has to go to this place, and then the second time it has to go to a different place. So how it remembers where it needs to go back to has got to be a dynamic kind of thing and not a static kind of thing. Do you know what I mean? It's not something that can be determined at compile time and just say, oh, at the end of f, we always go back to that place. Well, we wouldn't know where to go back to until the call actually happens. Is that making any sense? So now the bigger question is, how does the program do it? How does it know where it is supposed to go back to in the subroutine call and the return? Okay, so we'll attempt to answer the question in just a little bit. And the next section is a digression to talk about what a stack is. So instead of talking about the abstract concepts of a stack, which is last in, first out, we'll just go ahead and focus on the C code that I have included here. So we'll start with the C code like this part here. Okay, and we'll try to look at these 3 lines of code and go like, okay, what are they actually doing? The pound defined line is kind of the same thing as a const definition. So if you have no exposure to pound defined, you can look at this as const int stack size equals to 32 semicolon. Okay, it means about the same thing from our perspective, even though the mechanism is quite different. But from our perspective, we just look at this as a constant. And that constant is used in the second line. The second line says uint8 underscore t stack and then stack size in brackets. It's simply declaring a chunk of memory called stack. It is an array of uint8 or 8-bit unsigned integers. So are we okay so far with the first 2 lines? The first line says how big a stack is. The second line declares the space that we actually need for the stack. Are we good so far? The third line is defining a stack pointer. So the stack pointer is a pointer to a uint8, so it is supposed to point to some content on the stack. So it's supposed to point to one of the members of the array called stack in this case. So are we okay so far with these 3 lines? I haven't shown you the initialization, but this is what it is supposed to look like. Are we good so far? Okay. So the next part is a little bit confusing because we have to talk about where the stack, what the stack pointer is really pointing to, or what is the meaning of the stack pointer. That is the part that is a little bit difficult to explain, because there are several things that we need to consider. So the first one is this part here. To facilitate efficient use of instructions, a stack quote-unquote grows down instead of up. Okay, what that means is when we have more items added to the stack pointer moves down to a lower location instead of moving up to a higher memory location. That's kind of awkward, right? I mean, we don't usually do things that way. We usually use up the beginning part of an array as we need to, toward the end. But this one is exactly the opposite. We start using the end of an array and then work our way to the front of the array as we put more items into a stack. Okay? And then the second line, or the second paragraph, is also important. The stack pointer is assumed to point to the last item that we have stored, otherwise known as pushed, onto the stack. So the code to store something onto the stack is the next two lines in C. So we'll take a look at what those two lines are doing. We are referring to these two lines. Now, because the stack pointer is supposed to be pointing to the last item already stored, so the first thing you need to do when you want to push something new onto the stack is to go like, oh, we need to reserve the space for the new item first. How do you reserve for the space of a new item? You move the stack pointer down to a lower location. Are we doing okay so far with that? Because every location that the stack pointer is pointing to and up are already in use. So in order to get a new location to store something new, the first thing you need to do is to say, oh, I'm going to allocate a new byte on the stack for the new thing that I want to store. After you allocate that space for the new item that you want to store, then the second thing you want to do is simply to copy whatever you want to store on the stack to where the stack pointer is pointing to. Are we doing okay so far with this? Yes? It is just to emphasize that we are dereferencing the stack pointer. So the parentheses on the second line are not needed. Any other questions? Yep. Then you are out of stack. When you run out of stack space in any environment, you're in big trouble. Yeah, so you definitely don't want to run out of stack space. So that's a very good question. So we can, in the C code, you can actually test it and see whether SP is less than or equal to stack, which is the name of the array. Because if SP is less than or equal to stack, that means you have run out of stack, and your program really needs to stop right away because there's no more space on the stack anymore. Okay. So are there any other questions regarding these two instructions? So these two instructions are needed when we want to put something new on the stack, when we want to store something on the stack. It's otherwise known as a push operation. Is that okay? More or less? Okay. What if we want to do what we want to retrieve what is on the stack right now? Well, it's exactly the opposite. So you can see how this statement in C is exactly the opposite of this statement in C. And this statement in C is also the exact opposite of this statement in C. But there's also one more opposite. The order of the operation is also opposite. When you're storing, the first thing you do is to decrement the stack pointer, and then you store to that location. When you are retrieving, the first thing you do is to retrieve whatever the stack pointer is pointing to. So I'm putting back into register X. Then we increase the stack pointer because we want to reclaim that space that is no longer in use at this point. So is that okay? All right. So now we have talked about how to push something on the stack, which starts with reserving the space and then moving something into the space. How to retrieve an item from the stack, which is retrieving the item that is pointed to by the stack pointer first, Then we increase the stack pointer so that we know that, oh, that item is no longer in use. We just retrieved it. So is that okay so far? All right. So the last instruction is how we initialize the stack pointer. So this particular thing here is just the initialization of the stack pointer. Once again, remember what I said. The stack pointer is initialized to a high location initially. So when your stack is empty, which means nothing is stored on the stack, it is actually pointing beyond the last byte of the stack. Is that okay? Does everybody understand what the highlighted C code actually means? It's pointer arithmetics. So we are adding stack size to stack, which means we are actually taking the address of stack in square brackets stack size, which is one element past the end of the stack. So when the stack is empty, the stack pointer points 1 byte beyond the end of the stack itself. But that's actually consistent, okay? It doesn't sound like it makes a lot of sense, but it does make sense. Because remember, the stack pointer, quote unquote, points to the last item that we have stored. If you have not stored a single item yet, where is it supposed to point to? Do you see what I mean? It cannot point to something that is on the stack already because we haven't stored anything yet. Now, if you combine this with the first push on the stack, then it will start to make sense. In other words, you do the initialization first, which is the highlighted code at this point, and then you push the first item, which is over here. So you can see that we are not going to store anything to the byte that is 1 byte past the end of the stack, because we pre-decrement the stack pointer before we store. So by the time we store, the stack pointer really is pointing to the very last byte of the stack. We're not storing beyond the stack itself anymore. Is that okay so far? Okay. Now, how useful is a stack in computer science in general? Extremely useful, okay? So you might ask, well, what do you mean by extremely useful? Calling and returning makes use of a stack. The parsing of most programming languages involve the use of quote unquote a stack, or at least last in, first out. Okay. Let's see, what else makes use of the stack? All the parameters, they're on the stack. All the local variables, they're on the stack. Okay. So the stack is a very, very important part of computer science, not only from the practical standpoint, like in C, C++, and all practical programming languages, but also from the standpoint of theoretical computational theory. Because does anyone know who is Alan Turing? Okay, so he is the quote-unquote the father of modern computer science. Okay. And in his theory, he talks about automata or finite state machines and stuff like that. So he basically has a theorized machines, classes of theorized machines that can recognize certain languages. So one particular class of machine is called a finite state machine, which can only recognize regular expression. We talked about regular expression in this class already when we talked about scientific notation. Okay? And then the second class of machine is called a stack machine. And that entire class of machine handle basically all the programming languages that we are using today. And then there's a third class of finite state machines. They're called Turing machines. They're the most general machines that you can think of, in terms of theory. And there are things that you cannot even do with those machines. So you will get to those classes in a 4-year university as an upper division class. It's either called computational theory, and there's a separate name for that which I cannot remember, but computational theory is one way to refer to those classes. Okay, so getting back to the pragmatic stuff here, do we have any questions about what a stack is and how we use a stack? This is all good so far? Okay. So now we go back to talk about what is calling and what is returning and how it is done in assembly. Okay? This is one thing that I cannot show in C and C++ because the way C handles calling and returning is hiding all the details. So there's no way for me to show you the equivalent code in C and C++. It has to be done in assembly. Okay. The first chunk of code here, okay, let me highlight it on the projector. The first chunk of code is how we call a subroutine. So F and then open and close parentheses and then the semicolon in main translates to something like this, okay? The first thing we do, oh, by the way, we designate register D as our stack pointer. So the toy processor has no pre-designated stack pointer. It is just a convention that we use register D as our stack pointer, okay? So the first thing we do is we decrement the stack pointer, which is consistent with SP minus minus in the C code. The second thing we do is 2 instructions, because we cannot do it in one single instruction. We have to do it in 2 instructions. The first instruction is loading some value into register C, and then the second instruction stores register C to whatever the stack pointer is pointing to. Remember, register D is our stack pointer, and ST always dereferences where you're storing. Is that okay so far? Okay. So in the end, what this really means is line 1 is SP minus minus. The second line is star SP equals to C. Okay, which is something that we talked about a little bit earlier. So now the question is, what is so significant about L1 as a label? Well, we look at L1 as a label and go like, okay, it's defined here. It's defined right after the Jmp IF instruction. L1 marks where the subroutine is supposed to go back to. That is the significance of L1. Let me say that one more time, because this is really important. L1 as a label is a symbolic name of the address of where the subroutine is supposed to return to when it is done. Okay? So that is what L1 is. But how do we use L1? We store L1 on the stack. We push L1 on the stack. In other words, we're using the stack to help us remember where a subroutine is supposed to go back to. Is that okay? More or less? Okay. The jump F instruction is not really surprising, because this is how we continue execution. Remember, this code is in main, so in order to continue execution in the subroutine called F, we just do a regular jump. We just say JMPI unconditional jump to the label F. Then we continue execution in the subroutine F. Are we doing okay so far with this code? Are there any questions about these 5 lines of code? The only instruction we really haven't talked about is decrement, DEC, which is just decreasing the value of a register by 1. So is that okay? All right, cool. Okay, so now in subroutine F, when it's done, what are we going to do? Well, inside the subroutine F, inside the caller, at the very end of the caller, we have these 3 instructions. Let me see if I can move this up a little bit. Oh, I need to resize the browser first. There we go. All right. So at the end of a callee, or the subroutine that is being called, these are the 3 instructions that we need to execute. The first instruction is retrieving what the stack pointer is pointing to into register A. The LD instruction is the opposite of the ST instruction, and whatever is in parentheses is whatever we're dereferencing. So we are dereferencing register D because that's our stack pointer, and whatever the stack pointer is pointing to is now copied to register A. In C code, this is equivalent to A equals star SP. Register A gets whatever the stack pointer is pointing to. Is that okay? The second line is incrementing D, which is the same thing as SP++. Okay? So the pop operation is done by this point. The last instruction is something that we haven't seen. Okay? JMPA. A is not a label. A is the name of a register. And this is JMP, not JMPI. So now the question is, what is this doing? Okay, because I thought we only use a label to designate where we want to go, but this time we have a register. We cannot continue execution in a register, but we can continue execution where a register points to, right? So let's go ahead and check out JMP itself and see how it is described in the opcodes table. The opcode table, it doesn't keep the zoom ratio every time I go back to it, because I know what I need to do. I need to pin it, because I'm using a browser add-on that puts web pages to sleep when they're not used for a while. Okay, there you go. So we have now the jump instruction, and we'll zoom in a little bit. Okay, so this is the JMP instruction, which is different from a JMPI instruction. It does use a register. Register, X is a register, and it takes the place of XX in the binary opcode. Okay. And what about the description? It's unconditional jump. Okay, that part we know. But what about the C code here? PC equals X. That's it. It just takes a particular register out of the 4 from the register bank and say, oh, PC, update yourself to the same value. That's all it's going to do. Okay, that seems pretty simple. But what does the program counter do? What is the job of the program counter? What is its role in the execution of an instruction? Go ahead. It keeps track of the address of the next opcode to fetch. Okay, so the program counter is used in 2 of the cycles of the execution of an instruction. The first cycle is fetch. Okay, so in the fetch cycle, we look at the program counter and say, hey, program counter, point to the location in RAM where I'm supposed to get the next opcode. That's the fetch cycle. In the next cycle, which is called the decode cycle, the program counter is incremented, because once you fetch the opcode at that location, you need to move on so that the next fetch is going to grab the next opcode and it's not going to grab the same opcode over and over again. So that is the significance of the program counter. It points to the next opcode to execute, to fetch. Is that okay? So by changing the program counter to whatever register you specify as X, that means we are directly changing where we get the next opcode. Is that okay? So let's get back to the module. Nope, not this one. This one here. Okay, so getting back to here. So the effect of line 3, which is jump A, is really just saying whatever A has as a register is the address of the next opcode. We continue execution over there. So are we okay so far with the call and the return code in assembly? Is that okay? All right. So except for increment and decrement, which are pretty easy instructions to understand. One decrements a register, the other one increments a register. So those 2, I'm assuming that we can understand it relatively quickly. And the tricky one is the jump instruction. But all of the other instructions we have already introduced for, I'm thinking, at least a week, at this point. So I'm expecting you guys to already know what is LDI, what is ST, and what is the LD instructions doing. All right? So what do we do next? Well, we look at this and go like, this is all looking kind of okay on paper, but does it actually work? And if it does work, what is going to be changing in memory and stuff like that? Okay, so that would be the next question. So what I'm going to do with this class is a little bit different from my Monday, Wednesday class. I'm going to do something that has recursion in it. Okay? So we'll go ahead and write the code first, and then we'll assemble the code, run it in the simulator, and then we'll analyze a trace on the simulator and go like, oh, okay, so this is how it works. So we'll go ahead and write some code first. The first thing we need to do is to initialize the stack pointer, which is register D. Now the register D is supposed to point to the one location past the end of the stack. So the first question is, where is the stack? Well, you only got 256 bytes in the entire RAM. We know the assembler assembles from location 0 and up, right? So the first instruction is at location 0, the next one is location 1, and so on. So the first part, or the beginning part of RAM, is used for your program, and possibly some global variables. Oh, so that means we can use the end of the RAM as our stack. Does that make any sense? So the last location of the stack is location 255, or otherwise known as FF in hexadecimal, because that really is the very end of the RAM space that we have. Is that making any sense? So what is the location, what is the address of the byte that is just past the end of location 255? As an 8-bit number. That's the tricky part, because 255 plus 1 is 256, right? 256, that's easy peasy. Except 256 requires 9 bits to represent. But your address is only 8-bit wide. So what you do is you just chop and discard the most significant bit. Then we get what? What is 1, 0, 0, 0, 0, 0, 0, 0, 0, but we chop that 1 off. Then what do we get back? All zeros, exactly. So adding 1 to FF as a byte will get you all zeros. Okay? So that means the stack pointer should be initialized to a value of 0. Okay? So I'll just use the more obvious way to do it for now. Okay? So we just load 0 into the stack pointer D. And then we can say, okay, from here on, this is main. And in main, we have to set up a call to the subroutine. And then we'll do something kind of fancy here. We'll say, let's keep track of a counter. I'm going to use register C as a counter. How many levels of recursion do you guys want to do? I mean, anything past like 2 or 3 levels doesn't really help any further. So what about 3? Okay. So we'll have 3 levels of recursion. So this is a counter for recursion. I'll give you this actual C go later on. And then we are ready to do the first call to the subroutine, which is recursive. Okay. So now we say LDIA with main return as a label. And this is the way that I usually write it, so that I don't forget to define the label later on. And then we just replicate some code that we have seen earlier, which is decrement D. Okay. Reserve space on stack. And then an ST instruction, stda, store return address on stack. And then we perform an unconditional branch to the subroutine. Let's just keep the subroutine name as F. Okay, so we just call F like this. When it is back, then we're all done. Okay, there's nothing else to do in main. So now we have to write the subroutine F. So subroutine F is here. The first thing it's going to do is to check register C and see whether it is 0 or not. I'm not going to give you the code to test whether a register is 0 without using compare, because that's in your homework assignment. So I'm going to do this the long way. Okay, but in your homework assignment, you're supposed to do it in the kind of optimized, shorter way to do it. So in the long way, I have to load another register. I only got register B, or yeah, A and B are both available. So I'm going to use B here. So I'm going to load register B with a value of 0, and then we do a compare, and we compare B and C. The order doesn't really matter in this case, because I just need them to be the same. So now I can say JCI, if they are the same, go to some label. We'll call this label else. Okay, else is over here. If not, we're going to here. Now this is just my habit. If I do not perform a conditional branch, I want to comment on what does it mean if I do not branch. Okay, so I would just say that B register C does not equal to 0 over here. So if it is not 0, then we'll do a decrement C, and then we'll do the recursion. So when we do the recursion, it's the same deal. We load something with f return in this case. F return is a return label. We define it after this chunk of code. Decrement d to reserve a space on the stack. std with a, so we are storing the return address back into f in register in whatever the stack location is that we have just reserved, and then another jmp I to f. When we are back here, we can then jump around the else branch, so we go to end if, and then over at the else there's really nothing to do, so we say end if right here, and then we are ready to return. When the subroutine is ready to return, there are 3 instructions we need to execute. The first one is the LD instruction. We are getting back the return address from where the stack pointer is pointing to. The second one is to increment the stack pointer so that we deallocate the byte that we have just retrieved. And then we do an unconditional branch based on the register so we can continue execution. All right, so this is all in assembly code. Let me show you what the C code should look like. Okay, so the C code of F is like this. Or I'll start with main. This is the C code. The C code of main is to have a global variable. Okay, so imagine we have a global variable, and this time whether it's signed or not doesn't really matter. So we have a global variable called C, and then in main, we initialize C to 3. We call F, and then we just, then we are done. This is what main is. F, on the other hand, does not return a value, so it's void, has a void return type. And in here, we basically just check whether C equals to 0 or not. And, okay, yeah. So we check whether C is 0 or not, but the correct correspondence is we check whether it is non-zero or not first. And then the else branch deals with the case when it is 0. When it's 0, we don't have anything to do. If it is non-zero, then we just decrement C first, and then we perform another recursion, when another call to F itself. So this is the C code, and then the earlier part is the assembly code. Well, are there any questions about the C code? I have a question about the C code. Is this really going to end? If it does end at some point, what does it look like on the stack? So let's go ahead and first compile the C code first, and just kind of see what it's going to do in a debugger. So we do a Control-C, make a new file out of this, and save this one as a C file. So we save it in the temp folder. Let's call that test.c. There we go. And then we go ahead and compile this code. So let's go here. I think that's fine. Okay, so -g-1 all test.c-o test. Oh, doesn't like it because I forgot to do a prototype first. Okay, fine. We'll just do this is what is complaining. I didn't tell the compiler what f is. It's a function that has no parameters and it returns void. So that's basically what was missing, and the compiler complained about it. That was all good. So now we gdb test. We look at the program. We put a breakpoint at the very entry point of f, and then we run the code. Okay. So now we are at breakpoint 1. We're at the very beginning of the whole sequence of calling. And if we continue execution, we'll end up at the same line because it is calling itself. And we can always check what C is. C is 2 at this point. We continue. C is now 1. And we continue one more time. And this time C is 0. In other words, main has now called F. F has called F. F has called F. F has called F. Okay. That sounds awfully confusing, right? So let's visualize what we are talking about here. GDB has a command called bt, or backtrace. And this is what it looks like. It tells you exactly where we are. We are now in F on line 12. How did we get here? We got here from line 15 of F. How did we get there? We got there from line 15 of F. How did we get there? We got there from line 15 of F. How did we get there? We got there from line 6 of main. In other words, it keeps track of all the invocations all the way up to where we are now at this point. I think that's pretty handy. But now we have a bigger question, okay? Because there's only one function f in the entire program. How come there are multiple f's when we look at the backtrace? That's because, go ahead. Exactly. So there are two concepts involved here. When we say f, there are two concepts, and sometimes we are not clear which one we are talking about. When you read the source code in test.c, that particular f is called the definition of f as a function. Okay? It is static. Okay? It's just there for the compiler to read. What we are looking at here in the debugger, these are invocations of f. In other words, they are instances of f getting called. You can have one single definition of f in the source file, but any number of invocations of f at any particular time when the program is running. That is the difference of the concept. Now, to equate it to something that you probably have like some exposure to already, function f in the source file is kind of like a type. It's kind of like a class. Okay? It's a very static definition of something. What you're looking at here in the debugger, these are objects, okay, relative to classes. These are actual instances consuming memory locations and stuff like that. Okay? Yep.
That memory address.
Right?
In front of each app.
Yep.
So it's the same. So when you say it's an object.
They're the same because they're all reflecting the same point where the recursion occurred.
Like you said, each one's an object. It's not showing those.
It is not show. Well, okay, these are addresses that is coming from the quote-unquote class definition itself, and that's why they are the same. Okay. On the other hand, the actual, I don't really have any local variables, so I can't show you. But if f has any local variables, each one would be different in what we call frames here. Okay. So are we still doing okay so far with this? All right. Okay. So this program does work. Okay. If I continue execution, it will start returning, but it won't stop anymore because the breakpoint is at the entry point of f. So as we return, it just kind of go. It zips all the way back to main, and it's done. Okay. So there we go. Program is done. Because when we are backtracking, when we return from the last instance of f or the last invocation of f, it just keeps returning without stopping. Okay, so this may be a program that you can kind of look into a little bit more or single step through, just so that you can see what the C code is going to do. So getting back to the assembly code, okay. So now we look at this assembly code and go like, well, it's supposed to have about the same behavior as the C code, but using the toy processor. So we look at this code, and we just copy and paste it into the assembler. So huh? Oh, the C code? Wow, it's really short. I mean, you guys can just type it. When you type it, you might want to add your own comments too. If I have time at the end of today's lecture, I might upload it. All right, so now we go to source. And you can see that I had another sample program for my Monday, Wednesday class. That one is just based on whatever is in the notes. So the program that we are testing right now is based on the C code that I just showed you. It's just a little bit, just a tad more interesting. But it also helps to explain what recursion really is. All right, so this assembles just fine, and then we go to the RAM file tab, download, and what should I call this? Call return, okay, and overwrite what I already had here. And then we switch to LogicSim, Control R, reset the entire thing. And simulation is enabled. I'm just wondering why it's all in blue. So we load image, call return, and it doesn't like it. Might have to restart LogicSim because I think it's lost. Yeah, definitely lost. Okay, let's restart LogicSim. Okay, there we go. Right click, load image. And I think I know why it's lost too. It got lost because of tracing. When you perform tracing, it will do it correctly the first time, and then the subsequent traces sometimes will just, it just lose track of things because of that. Call return. There we go. All right. So if I just Control K and let the program execute at full speed, it will just get to the halt instruction, but you won't be able to see anything actually happening because it's going to be happening so fast. So what we need to do is to use the logging ability to kind of keep track of a few things so that we can analyze after the fact. There are quite a few things we want to track in this case. We'll track the program counter. We'll definitely want to track some of the registers. We can track all of them, okay? So we'll track register A, which is kind of used as a scratch pad for the most part. Register B, which is only getting the value of 0 for comparison. Register C is the counter. It starts with 3, and then at each level of the recursion, it is decremented by 1. So it will eventually get down to 0. And then register D is also very, very important because that's our stack pointer. We want to keep track of the stack pointer and go like, well, how does it keep track of all of these things? And then we also want to track a few locations in RAM. So we go to the RAM component, and we want to keep track of the last few locations because remember the stack grows backwards. So we want to track the last few locations. How many locations do you think we need to track? In other words, how deep was the recursion? So the first call is when C is 3. Okay, so 3, 2, 1, 0. So 4 levels of recursion. So that means we need to track location 255, 254, 253, and 252 for sure. And I'll track one more, okay, just to be sure. Or maybe 2 more, doesn't matter. Okay, now we go back here and we want to change the base. Because by default it tracks everything using base 2, which is not very handy. So we'll change everything back to base 16. There's no way to select, well, I have never tried. Let's see. Can I, nope. There's no way to select a whole bunch and change the radix all at the same time. There might be a way to change the default radix, but not when it's already here. Okay, so it's all done. We go to file, and then we want to log everything to a file. Let's call that call return.tsv for tab separated value. Click save. We overwrite whatever I already have. Okay, and then we can close this window. And now we just go do a Control K to start tracing, to start the execution of the program. So here we go. And it is all done. Okay, so when it's all done, we can double check and make sure that the program counter is not moving anymore. And we also want to double check that the microcode pointer is not moving either. So neither is moving, so we know that the program is now at a halt instruction. Control K again to stop the simulator. And this time I'm even going to exit the simulator because I know it's going to have a problem if I continue to use it from this point. So now we want to take a look at the trace. And the best way to look at it is to use a spreadsheet program. And I'm using LibreOffice because LibreOffice is a lot faster compared to using the Google spreadsheet. So that's the reason why I'm using this one. So we'll go ahead and open call return.tsv. And it already knows that it's tab separated, which is cool. Quote fields as text. Okay, let's click that. And then click OK. It's still doing the conversion into numbers, which is not what I wanted to do, but that's fine. This is register A, B, C, D, location 255, 254, 253, 252, 251, 250. I'm doing this, to so that I can shrink how much space is needed by the columns, because otherwise it's really, really hard to watch the entire thing, to see the entire thing. There we go. Much easier now. Okay. So when we look at this trace and go like, okay, kind of cool. This is where we end up at. Okay. So the program counter. Okay. Let me try another trick here. I'm using this feature so that the heading of each column is still visible as I scroll the rest. So we can kind of see that the program stops at location 0A. Or 0B, when the program counter is 0B, the whole thing stopped. So what do you think is the address of the halt instruction? Remember, by the time we see the effect, the program counter has already incremented because of the decode cycle. So that means if we see the program counter is 0B, it means the location of the opcode is 0A. Okay, so we can do some double checking here. Okay, so we go back to the assembler. Where's the assembler? I did something earlier to mess it up. Okay, so getting back to the assembler, we go to the Assemble tab so that we can look at the addresses. All right, so we are looking at the halt instruction on line 10, or row 10 in the spreadsheet. And we want to find the address. And the address is 08. Okay, well, so the program counter is very useful. So now the next question is the program flowing the way it's supposed to? So we look at the program counter. Okay, we kind of ignore everything else except when we see some changes in the other columns. So we look at the program counter. It goes from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. They're all going in a sequence, except from here, it just goes like bing. It went from location 9 to location B. That doesn't seem very sequential to me. So what just happened? That's the call. That's our call. Okay. So in a function call, what happens is execution continues in the subroutine. So everything up to location 9 is still in main. But I'm saying that location 0B is the first location in the subroutine. Well, how do we check that? We go to the Assemble tab of the assembler. So let's double check. And we're looking at label F, and label F is indeed at location 0B. Remember, the label is a symbolic name of the byte that is defined right after that. So 0B is the address of that byte. Okay. So getting back to the spreadsheet. All right. So that means this transition here is significant because this is the actual call. This is the last portion of the call. But I vaguely remember there's a whole bunch of instructions before the Jmp instruction when we call a subroutine. What did those things do? So we look at changes to the registers and also memory locations now. So before this transition, we see the first change was to register C, but that's okay. We are just setting up a counter to be 3. And that's why your register C had a value of 3. So that's fine. That's pretty cool. Then we have on row 10, we can see that register D is now FF. That's because of the decrement. Decrement D changes register D from 0, 0 to FF. Okay? What did we do with register D? We store something to where it points to, didn't we? There's a store ST instruction. So that's why we see that location 255 is now getting a value of 0A. Is that okay? That is the label, or this is the return address. This is where the subroutine is supposed to go back to. Okay? So that is supposed to be main underscore RET, the label. Okay? That's supposed to be 0A. So let's check whether that is the case or not. So we look in here and we look at main return. That indeed is location 0A. So that's how we store the return address. All right, so getting back to the spreadsheet. What is going on after this? Well, we got into the subroutine, and the first thing the subroutine is going to do is to check whether register C is 0 or not. Okay, so we will do some compare, and at some point, it's going to do a recursive call because it is not 0. So we want to track the stack pointer. You can see how the stack pointer changed between these two rows. Because on row 24, the stack pointer is FF. On row 25, it is now FE. This is another decrement of register D because we are calling F from inside F itself. In other words, it doesn't really matter who you're calling from where. The mechanism of calling a subroutine does not change. What are the steps for calling a subroutine? Push the return address and then continue execution in the subroutine. And that doesn't change at all, whether it is recursive or non-recursive. So over here, we are decrementing the stack pointer, and then we store 17 or 17 in hexadecimal as the address to return to. Do we know whether 717 is actually the location to return to? How do we know that? Well, we look into the assembler again. So we look into the assembler. This time we're looking for F underscore RET, which is the return address within F. And it is defined here. And you can see that the address is indeed 17 in hexadecimal. Okay. After we push that, what happens to the program counter? It goes like 14, 15, 16, back to 0B. 0B is already here, see? Because of the recursion. So every time you perform a recursive call, it simply pushes the return address, and then it continues execution at the very beginning of the subroutine that you're calling, which just so happens to be the same subroutine that you were in. But don't let it bother you. It doesn't really change the mechanism at all. So this is basically the second invocation of the subroutine. So I'll just be quick here. So in the second invocation of the subroutine, you can see how eventually another location of the stack is used, and then another location of the stack is used. So we'll end up with 4 locations of the stack. 3 locations. 4 locations because 255 is 1. And then we'll start to return. In the trace, how do we identify the returning from the subroutine? It's going to be a sudden change of the program counter. So we're looking for some sudden change of the program counter. I would say this is a pretty sudden change of the program counter. Okay. And let's see. We are also looking for the stack pointer to start to increment as we return. So you can see how it's incrementing from here to here. And then the program counter goes from 1C back to 17. That is the return. 1C is 1 byte past the last location of the last instruction of a subroutine. 1.7, we already know what that is. That's the label of where we are supposed to return to. In other words, this exercise, okay, this particular program, is really illustrating the mechanism of calling and returning in assembly.